Okay, so I want to again look at some things we did last year and maybe refresh our memories here a bit about how to graph a polynomial function without a calculator. And so again, some of this might look super familiar, some of it might seem challenging, and like you might not remember it at all solving this. So I kind of want to walk through these several examples together, just again to make sure we're all on the same page. So and our goal, you should keep in mind, our goal is to be able to graph these and sort of predict the behavior of these functions without a calculator. Okay, and so there are two different kinds of behavior we want to talk about. One would be like local. Oops, sorry. Local behavior. So so things that are happening around the x-axis, but then also end behavior. What's happening at the extremes, like infinity versus negative infinity. Okay, so this very first function here, right? So I want to look at that, and I know that there are two x-intercepts, one at 1 and one at -3. And I know that because those are the values that make those quantities equal to 0. So as I sketch this, that's my starting point. That's kind of like what I would refer to as like the local behavior. So the local behavior, what's happening near some points. So definitely at x equals 1, we know there's a 0. And at x equals -3, there's another 0. Okay. Now the behavior at these zeros, though, could be a couple of things. Like it could intersect right through one way or another way, right? But at the same time, it could also just be tangent. It could just be like a touch and go, or it could have been like tangent below it, right? Touch and go. So I want to look at the behavior of those zeros, and it has everything to do with if it's even or is it an odd exponent. Oops. There we go. So like x minus 1 squared, that's an even number. That means the behavior at 1 is going to behave like an even exponent. And you can think about an even exponent. That's like a parabola, right? So an even exponent, if that is an even exponent, it's going to behave like a touch and go, like a parabola. Now it could be opening up or it could be opening down, but at least the behavior is just going to sit right there on the x-axis. Okay. Now, the even powers, the higher the power, what that does is it basically it flattens out the curve. So it actually gets to 0 quicker, which is something that's really important in calculus. But for us, is not as important, other than just recognizing that you want that to be an even value. Sorry, like a parabola. Okay, if you're an odd value for your exponent, and sometimes I'll refer to that as a multiplicity, right? So if you're an odd value, so at -3, the behavior is going to behave like an odd, like an odd valued polynomial, like a cubic function or a linear function, or a fifth power function, and so that intersects. So it's going to intersect or it's going to cross. And if it's linear, it's going to cross just like that. If it's third power or fifth power or seventh power, it's going to do like a little squiggle, right? I think is what the Hatu teacher said, or like it's going to intersect as if it were like a cubic. Now it could also intersect this way, or it could intersect down like that. So the behavior locally is going to depend on the multiplicity, or the even versus odd powers. So I'm going to write that word down, multiplicity, in case I reference it again. But that multiplicity simply means looking at that exponent. Okay. Now, you also need an overall power function. Okay. And a power function is when we start looking at the end behavior. Okay. If you were to distribute distribute this square and this cube and put everything together, the highest power would be a fifth power. You have an x squared, x cubed, multiply them, you have an x to the fifth. So I would say my power function for this problem is x to the fifth. So if I were to zoom out and not see the local behavior and only see the end behavior, I should know something about a power function that's x to the fifth. Okay. Well, all odd power functions that are positive valued have a certain characteristic way of opening. So I'm going to say if you're a positive odd power function versus a negative odd power function, okay? If you're a positive odd power function, your shape is going to look something like this. So let's go ahead and change. I'll make this a little bit darker for the XY axis. Something here, okay? So if you think about what is the characteristic shape of a cubic look like, it's going to look something like this. Where notice where you're starting. You're starting down here and you're ending up here. And when I say positive odd, I'm saying that the fact that the coefficient here is a positive value. Okay, a negative odd. Had there been a negative there, you're just going to flip that over. It's going to look something like that. So if you have a power function whose highest power is odd and it's a positive value, the overall shape's going to look like this. Or like if it's a negative, the overall shape's going to look like that. Okay. Now, it's probably good to know what if you were even, right? So maybe we should also add that over here. Okay, if you're a positive and happen to be an even exponent, which I'm taking a look, looks like the next example might have that, versus a negative even power, what does that look like? Well, then you want to think about, parabolas. If you have a positive quadratic or a positive fourth power or a positive sixth power, what's going to end up happening is you're going to open up. That's a positive value. Or if it's a negative coefficient, then you'd be opening down. But notice it has that touch and go characteristic shape. And again, the higher the power, as long as they're even, the higher the power just means it's going to have a little bit of a flatter surface here. In other words, it's going to get to zero much quicker. Okay, so that's sort of like just a little bit of background that we definitely need to know, analyzing a power function. What's the overall shape? What's the overall trend that's going to happen? Okay, now our problem back here said we have our power function. If I see that's squared, that's cubed, that's fifth power total. So my power function is going to be x to the fifth power as a positive value. That means I know I have to start in the lower left down here somewhere and end in the upper right. Okay, so I know my end behaviors here and here. So as I start to graph this, I'm going to come from the lower left side. I know I'm approaching -3. And the behavior of -3, that multiplicity is odd. So if I have that odd multiplicity, I know I'm going to do this little kind of squiggle. So I'm going to start in the lower left, approach that -3 and do a little wiggle, right? A little cubic shape, and then go up a little bit. And then I know I need to come back to 1 as a 0, but the behavior of that is even multiplicity. So I know it's gotta come in here and bounce there and go back up like that. And it's good that it's just a bounce, right? It's good that it's just doing that parabolic shape because I know my end behavior says I have to end up there. So the overall trend of this graph would be starting lower left, going through -3, doing nice little some kind of curve, and up we go. Okay, it's just a sketch, and there's some details that we don't know, and that's okay. Like for example, I don't know. I don't know. Go to orange, I guess. I don't know the peak. I don't know how high that is, and that's okay, right? I don't have to know that. I don't know like where does this start to transition from like opening up to opening down, and that's okay. Now there is one thing that I do know, and that's the y-intercept. I could find the y-intercept because I know I could let x equal 0. If you let x equal 0, you get 1 times 3 cubed is 27. So I do know that point is 0, 27. So I can label that, right? I can find the y-intercept. I found the x-intercepts. I wrote the power function, right? The power function was the function that if you were to expand all of this, the lead coefficient would have been x to the fifth, the highest power. Okay, but again, it's a sketch. It tells us some good things about the graph, but it doesn't tell us everything. And like I said, that's okay. Okay, so this is a really important example. There are a lot of things in this example that are more than just example 1, especially the this little bit of a description down here in green. So my computer there readjusts. This description down here that I boxed in green of knowing that behavior. So I'm gonna pause the video and actually create a second video for the next example. And I'm gonna sort of talk through a lot of this. And that's sort of the expectation that you need to be at a place to be at when we do these for homework and quizzes.